Good evening, students. I'll start with the class. In the previous class, we were doing the topic collision. So we had seen there are two types of collisions. One was elastic and the other one was inelastic. Here we saw in both the cases, anyways, momentum was conserved. This is common for both. Means what? Initial momentum is equals to your final momentum. M1 U1 okay plus M2 U2 was equals to M1 V1 plus M2 V2. For both the cases it was same. Okay, but for kinetic energy, okay, or the energy, here what was happening? Here it was conserved, here it is not conserved. Kinetic energy is conserved. Same thing, only thing you have to use half. Whatever was in your initial kinetic energy remains same after collision also. No energy is lost in the environment in any form. No heat produced, no sound produced, nothing. Okay, whatever was before collision remains after collision. So this was the thing for elastic. For inelastic, we knew that this is initial one is not equal to the final one. So there is basically energy loss over here. Here there is no energy loss. 100% there is some energy lost over here. Okay, so basically in inelastic, remember that energy is lost in some form of the other. We had derived, okay, one this, what is that we had seen that starting velocities and remaining velocities always remain the same. Change in u1 minus u2 is always equals to v1 minus v2 or v2 minus v1, whichever way. And then we derived some equations for velocity v1 and to find velocity v2. We saw the two cases also. That was for elastic, whenever this is equals to this one. Now we'll see for inelastic collisions what happens with this to calculate this energy loss. Now under inelastic, no, in elastic you know that there is always a energy loss. Now there's something called as perfectly inelastic. Perfectly inelastic, no, what happens is if this one was moving suppose with v1, okay, and this one was moving with v2 suppose, so this m2, this was moving with v2 or u1 and u2 initial, no, we can consider u1 and u2. This is before collision. Now what happens, suppose they collide at collision, this is second case. What happens, this fellow comes and hits this one. Now definitely in the previous case what was happening, they will have different velocity. A perfectly inelastic, what happens is this fellow gives entire energy of his to this one. He submits all the energy to m2. So after collision what happens is they both move at the same speed. What happens, the entire energy from whatever was moving is transferred to the second body. when they both move with the same velocity, okay, or either they will stop, whichever is the case. So it's perfectly inelastic collision. Entire energy from body 1 transferred to body 2. Example, throwing a mud ball on the wall sticks to the wall. I'll explain this. A man jumping suddenly. Okay. Now this is the example. So I'll explain to you the second example first. Now this man was running. There's a cart. Okay. So this is a person, and this is a moving cart. Both are moving. Now what happens? This one is also having some velocity. This one is also having some velocity. Now he suddenly jumps. So once he jumps, what is going to happen? He comes on the cart and he's standing there. Now what happens? Both are moving at the same velocity. That is v. So what happened basically? He transferred his entire energy to the cart. Okay, now they are both moving with the same velocity. Now he is not having his own velocity. He gave it everything to the cart, and now cart is taking him. Here what was happening? They were having initial separate velocities. Now in this. So this is a case of perfectly inelastic collision. Okay, so where the entire energy from one body is transferred to the other one. Consider this one. There's a wall. This may be at rest. Doesn't matter. Okay. The mud ball is moving. U2 may be 0 because it is at rest. Now what happens? The moment this is moving, it goes and sticks to this. So it's not moving. Now its total energy got transferred to the wall. So whenever it sticks to the wall, all the energy is lost. Okay. And now it is not moving. It stops moving after sticking it to the wall. So all the energy gets transferred to the wall. So in perfectly inelastic collision, maximum energy loss takes place. Okay. So in perfectly maximum energy loss. So let us calculate that energy loss. We will derive energy loss for perfectly inelastic collision. So this is the diagram. condition 1 before collision. Or you can first draw like this and then down. Remember that person jumping on the cart example, they both have the same velocity. So same like the previous derivation, you just have to write this in your own words. Let two bodies of mass m1 and m2 move with velocities u1 and u2 respectively. After collision, two bodies move with same speed v. Let the two bodies of mass m1 and m2 move with velocities u1 and u2 respectively. After the collision, the bodies move with same speed v. We know that whether it is perfect elastic, whether it is inelastic, this momentum is always conserved. In both the cases, momentum is conserved, only energy is lost. Momentum is conserved means m1 this, what is that? Initial momentum equals to final momentum, or best option is momentum before collision is equals to momentum after collision. This is the best way to write. m1 u1 before collision is equals to m1 v1 plus m2. Now what is happening? There is no v1 and v2. Both are moving with the same this. So this is also having v, this is also having v. There is no separate v1 and v2. Both mass m1 is also moving with velocity v, and m2 is also moving with velocity v. So now here basically v is common. So take out v common. So if I want to calculate this final velocity v, what will happen? This is nothing but multiplication. Take this entire thing down. So you'll get the formula for v. With this, it comes down. V. This is the velocity v for inelastic collision. Now we'll calculate the energy loss. You can mark this as equation 1 and So we'll say let E1 be total kinetic energy before collision. Let E2 be the total kinetic energy after collision. So you know that what is total kinetic energy before collision? E1 will be half the square, no? Half the square. After collision will be half m1 v1 square is half m2 v2. These are the kinetic energy. Half mv square is the formula. So velocities before collision are u1 and u2. That's why I'm using u. So these are the kinetic energies after collision. But now in this case, what happens? I'm using for perfectly in collision this. So both cases I'll take it as v only. I'll not take it as v1 and v2 because I told you both are moving at the same velocity v. Initial, definitely they're having different. So just look at the diagram, you'll understand. Before collision, this is so u1 and u2. But after collision, both are having same v. So that will be, you can take out half v square common. Or you can write other side also. Half I'm writing this side just for the simplicity of later solving. V square I'm writing this side up. Okay. Half m1 mass into velocity square. Instead of writing it this side, no, I just wrote it this side. So that's E2. Now we have to calculate energy loss. So what is energy loss? Nothing but change in E1 minus E2. Okay. Change in energy loss is the difference in the energy. So half, just substitute what is E1, this whole thing, minus U2 is this. Now we know what is the value of V from equation 1. Okay. So right there, put value of V from equation 1 over here. You know the value of V is this. So substitute it here. So it will become square because we want V square. So this, the whole square it will become. V value was what? There is a square term. Basically it's V square. Now this square will belong to both the terms, numerator as well as denominator. So separate it out. This square give to the numerator also. Okay, this is like a plus b the whole square. I'm giving it to the denominator also. So if it was like a upon b square, it's like a square upon b. So this square belongs to numerator also and denominator also. So I just separated out the square for numerator and denominator. Now basically it's the same thing, multiplication. So this is same as this one. So one square will go. Square means what? Writing two times, m1 plus m2 into m1 plus m2. So one of them will cancel with this one. So they are same terms, m1 plus m2. And if you notice, everywhere half is common. So I'll remove this half out. So what remains is m1 u1 square. This half also is gone out. So what basically remains is half I've taken out. This is a minus, no? This is minus. Now use a plus b the whole square formula. This was for v, no? V value was what? Just check, there was no square. I'll just copy, no? No one notices also. For momentum where there was square. Just check. There was no square for that. If you all find something different, you should always bring it to the notice. Just simply don't copy. Okay, there was no square. This was the v value. m1 u1 plus m2 u2 upon m1 plus m2. So that inside that square is not there. That is what I remove. Now it is a plus b the whole square. So what is a plus b the whole square? A square. First I'll write this. A square. So a square means everything will get squared. One second, current went. A plus b the whole square will be, there's a shadow which is coming through because from the other side. A square plus 2ab plus b square upon m1 plus m2. Now this minus sign belongs to all the terms. All the this will get negative sign. In this what we can do? We can cross multiply here up. So it will get multiplied to both the terms on top. Just cross multiply. This will get cross multiplied to these two terms. So this will be half m1 plus m2 into m1 u1 square plus m1 plus m2 into m2 u2 square. So after cross multiplying, this whole thing will come in the denominator, m1 plus m2. And this open up the bracket, so this will be m, then minus 2 m1 u1 m2 u2 minus m2 square u2 square. Just multiply this inside now. m1 square u1 square plus m1 m2 u1 square so no? Then m1 m2 u2 square plus m2 square u2 square then minus m1 square u1 square upon m1 plus m2. Now whatever is getting cancelled, you can cancel. Due to no. So this will get cancelled. This and this will get cancelled.
Miss, can you please shift the lamp? Can't see the board properly.
The problem with this current is even the charging point doesn't work. I have already a backup, but that is also not working everywhere. It's a current fault. That bulb is also not working. Okay. So if you notice, in the next way, everywhere m1, m2 is common. So in the next step, just take out m1, m2 common everywhere. From all the terms, take out m1, m2 common. here back. So everywhere take out M1, M2 common. Half M1, M2 I'm taking out common. U1 square plus U2 square. Okay, from here. M1, M2, everywhere you take out common. There. Okay. And then this denominator is there. M1 plus M2. So I'll just write it here. So basically what is this formula? A square minus 2ab plus b square. So I'll just arrange it in that form. U1 square minus 2u1 u2. This is basically in the form of a square minus 2ab plus b square. You see? So what is a square minus 2ab plus b square? A minus b the whole square. So this is your final formula for energy loss. U1 minus U2 the whole square. So for perfectly inelastic, if you are asked to derive what is the energy loss, so this is how you have to derive. And that will be your final answer of M1 M2 upon M1 plus M2 into U1 minus U2 the whole square. Okay, there's one case. Let's suppose this is at rest. This is a special case. M2 is at rest. So U2 will be 0. So both will check momentum as well as this. So what was velocity formula? For both the formulas will check. V was what? M1 U1 plus M2 U2 upon M1 plus M2. So in this case, put U2 equals to 0. Just write it on top because otherwise because of the flashlight not visible. So this is the formula for V. U2 is 0. From this case, so put U2 as 0. M1 U1 so V is just M1 U1 upon M1 plus M. I put U2 as 0 in that formula because the case is when the second body is at rest. Same way, for energy loss also you write the formula and wherever there is U2 put it as 0. This is for velocity formula. Now for energy loss formula, for the same case. So what would be the energy loss? We just saw it is nothing but half m1 m2 upon m1 plus m2 u1 minus u2 the whole square. So put u2 equals to 0 in this case also. The energy loss will be half m1 m2 just u1 square, because this part will be 0. u2 will be 0, so it's gone. So this will be the energy loss formula for this case where second body is at rest. Okay. There were some problems actually remaining. It's very difficult with these conditions. So for you all also it will be difficult. First of all, it is to attend online and then so much of distraction. Just some only last few problems were left in the class. Check. What y'all want me to do? I'll continue with the problems, or I'll record a separate class and send y'all once current comes. Because I don't know whether that shadow is disturbing y'all too much or not.
Miss, record and send.
Okay. Only problems are left. Otherwise, from the theory part, derivations part, this is done. Okay. So only some 4-5 problems were left. So I'll just do a recording on that the moment current comes, and then upload it on the group whenever you'll get time. You can just go through it. Because that shadow will be too much. Because this is very hot here for me also to focus, very difficult. Okay. So from the derivations point of view, these are all the derivations. Okay. Let's stop here.